Hi, in this video we're going to look at an introduction to the work on vectors. Some of this should be familiar to you, but it's still the starting point for the work that we need to do for the A2 course. So first of all, vector notation. We've got a grid that's showing points A and B. Now, if I want to go from A to B, I'm going to represent this as the vector AB. So it'll be the two letters AB with a line, an arrow above it. Going from A to B, I'm going in a certain direction. I've also traveled a certain distance. So this vector has both magnitude and direction. Vectors always have magnitude and direction. We also talk about things called scalars. Scalars are quantities that only have magnitude. And so we use them when we want to increase the size of a vector. We'll talk about a scalar being used to increase the size of a vector. Now, vector can be written in column format. And the two numbers that we're going to use are going to show the movement from A to B. We've got two numbers here. The number at the top represents the movement to the left or to the right. Because it's negative, it's going to be a movement to the left, whereas the number in the bottom is going to show the movement up or down. Because it's positive, it's going to be a movement up. This is referred to as a column vector. If, however, we're going to go from B to A, we're traveling in the opposite direction. And so now I need to think about my vector in a slightly different way. I've moved 3 places to the right, so it's going to be a positive 3. And I've moved 2 places down, so it's going to be negative 2 at the bottom. So the vector AB and the vector BA are different vectors. One's going in a certain direction, the other one's going in the extreme opposite direction. However, we can say that the vector BA is going to be the same as minus the vector AB. If I go and multiply that out, I'll end up with the same vectors. Now, sometimes vectors are going to be used by a single letter. Normally in textbooks, you'll see this being typed in bold. If you're writing it, then you normally would put a little line underneath it, underneath the letter, to indicate that we're dealing with a vector. If I've got a number in front of that, it means I'm going to take that vector and make it twice as long. So that is simply a multiplying factor that changes the magnitude of the vector. If it is a half, then it would be a vector in the same direction, but only half as long. And if it was minus root 2a, well, then it's going to be a vector that's in the opposite direction. The minus is going to talk about it being negative. Change the direction, and root 2 is going to be the magnitude of it, about 1.41 times a. So if we look at this little applet, we can see the effect that k has, a multiplying number, on the vector a. If I go and increase the size of a, then I'm basically creating a new vector that's going to be parallel to the original vector a, but the multiplying factor that I have in front of it is just going to increase the size of it. Likewise, if I decrease it, then I'm going to make the vector smaller until it's a point where I get to making it negative, and then it's going to go in the opposite direction to the original vector. Here I've got two new vectors. I'm going to call them vector A and vector B. If I want to add these two together, what I need to do is to shift the vector B to the end of vector A, and then look at the route that I've traveled as I go from B and add it onto A. A plus B is now going to be the sum of those two vectors. I've gone all the way along A, and then I've traveled all the way along B. And I could have made that with one simpler journey, and that's simply this vector over here, the vector A plus B. This also holds for subtraction. We need to think of subtraction, A minus B, as being the same as the addition, but the addition of the negative vector. So I'm going to think of the vector now as negative b. So I'm going to have to turn it around, put it to where the end of a is, and now I can see my new route that is what A minus B will end up as being, that distance over here. The diagram shows two vectors A and B. They're going in opposite directions, so B is going this way, A is going that way. So if we think about this and that, add them together, then we're going to get the vector A plus B. I'm going all the way along A, adding it to B. There is the vector A plus B. Adding vectors is not the same as simply adding their lengths. We use the column vectors. The column vector for A is 4, 3. I've moved 4 across and 3 up. The column vector for B is minus 5, minus 1. I've moved 5 to the left and 1 down. The resulting vector that I end up with, A plus B, this one over here, has gone 1 place to the left and 2 places up. If we take a look at the numbers that we've got there, I can get that final vector over here, minus 1, 2, by adding the two components together. So if I add the x components, the horizontal components together, 4 minus 5, I'm going to end up with minus 1. And if I add the vertical components together, 3 minus 1, I'm going to end up with 2. And that was my vector for A plus B. We can generalize this by thinking of the components of the two vectors as being x1, y1 for the first vector, x2, y2 for the second vector. When we add them, we simply add the x components together, add the y components together. Likewise, if we're subtracting them, then we're simply going to subtract the x components, subtract the y components, and that will give us our resulting vector. Some examples about how we go and add vectors together. So if I think about the vector A and AB in terms of P and Q, P being a vector that runs along this line over here, Q being a vector that runs along that line over there, I want to go from A to B, then I could either have gone up that way and across there, that would be a P and that would be a Q, or that would be two Qs, or I could have thought of it as two Qs going across and one P going that way. So I can write AB as being P plus 2Q, or I could have written it as 2Q plus P. Either way would be fine. I still get from A to B. If I think about BC, I've got to go 2 across like that. So that's 2 in the direction of Q. So that's going to be 2Q. And then I've got to go 3 along the vector direction that P is, but in the opposite way. So this is going to be 2 Qs, and that's going to be minus 3 Ps. So I can write it as 2Q minus 3P, or I could write it as minus 3P plus 2Q. CA is getting myself from C across to A, means I'm going to have to go in this direction along here. That's opposite the direction of Q, so these are going to be minus Qs. So I'm going to have minus 1, 2, 3, 4 Qs. But then I'm going to be going in the same direction as P, so there'll be plus 2 Ps. So going from C to A is going to be either 2P minus 4Q or 4Q minus 2P. If I join all of those together, and I think about what my result is if I go AB plus BC plus CA, well, AB will give me from A to B, BC will give me from B to C, and CA gets me from C back to A. I've got back to my starting point. If we think about adding all those vectors together, we end up with the 0 vector. The 0 vector gets us back to where we started from. To look at some examples of where we're going and adding some vectors. Here we've got 3 different vectors, A, B, and C. If we write each of these as a column vector, A is going to be the column vector 1 to the left and 4 up. So that's going to be minus 1 over 4. B is going to be 3 to the right and 3 up. So that's going to be 3 over 3. And C is 4 to the left and 2 down, so it's going to be minus 4 minus 2. So if I think about adding A and B, all I have to do is add their various components together. minus 1 plus 3 is going to give me 2. 4 plus 3 is going to give me 7. That's going to be my resulting vector 2, 7. If I wanted to see what c minus a was, all I have to do is take the components of c and a and subtract them from one another. We just need to be careful now about the double negative that exists there. So I've got minus 4 minus minus 1, in other words, minus 4 plus 1, in other words, minus 3, and then minus 2 minus 4, which gives me minus 6. And if I join the whole lot together and say, right, a minus 2b plus 3c, well, I'm going to have to multiply the vector b by 2, so the components are each going to be doubled. Whereas for c, I'm going to multiply them by 3, so they're going to be tripled each. So we now have the components that look like that, and when I add them together, I simply go and add the relevant vertical and horizontal components together. And that gives me a final vector of minus 19 minus 8. Now, if we talk about the magnitude of the vector, we're talking about the length of the vector basically, and we need to recap some work that we did with Pythagoras from back in the 4th form. So if we have this vector v that's in column form, a over b, so a horizontal component of a and a vertical component of b, we can work out the length of v by using Pythagoras. So the magnitude of v, the length of it, is going to be determined by the square root of a plus b. So if we keep that in mind, if I think about the magnitude of the vector r, that is the column vector 6 minus 8, there is the vector r. I've gone 6 across and I've gone 8 down. So if I use Pythagoras, it's going to be the magnitude of r, and we recognize the magnitude of r by having these double lines around either side of r, and that's going to give me the square root of 6 squared plus minus 8 squared, in other words, the square root of 100, which is 10. So the length of the line r, or of the vector r, is 10. Likewise, if I look at this one over here, it's got a horizontal component of minus 5, a vertical component of 9. I plug that into the Pythagorean formula, and I come up with a number 10.2956, which approximates to 10.3, to 3 significant figures. So the magnitude of the vector is its length. We said vectors also have a direction. The components of the vector, especially when it's in column format like this, will allow us to work out what that direction is. We're going to use a bit of trig to do this. So we know that this lies within a right angle triangle, and so if we want to work out the size of this angle over here, we're going to use the two components, the vertical component and the horizontal component. B over A, which you'll remember from your work with basic trig last year, is the tan ratio, and so I can calculate the angle over here by saying tan to the minus 1 of B over A, and that'll give me the direction. So we're going to use this formula to work out the direction of a vector. So if I've got my column vector 12, 5, a diagram is always useful so we know which way we're working, how we're going, whether we're going up, down, left, right, wherever it is. So now we know the vertical component is 5, the horizontal component is 12. So from the diagram we can say tan of theta is 5 over 12. And so if I want to work out the value of theta, simply going to be tan to the minus 1 of 5 over 12, or 22.6 degrees. Different vector here, d is minus 7, 3. Again, a diagram is useful. Minus 7 means I'm going 7 to the left, 3 means I'm going 3 up. In other words, the tan of that angle in this diagram over here is going to be 3 over 7. So that's going to give me an angle of 23.2. However, the angle that we're looking at is going to be this one over here, not the one inside the little triangle over there. So we need to take that away. We need to take that angle away from 180, and that's going to result in the angle of 156.8. That is the direction of that vector. Notice we're measuring it in an anti-clockwise direction from the x-axis. Right, what I'd like you to do now is to go to the Vectors Introduction lesson, find page 7, and practice your skills here with the magnitudes and the angles for each of these given vectors over here. So go and do that now, please. Right, hopefully that went well for you. Now, sometimes a vector is given with its magnitude and direction, and we can then use that to convert it back to its component form. So say I've told you that a vector has a magnitude of 7 and a direction of 25 degrees, and they ask you to write this in component form, in other words, in column form. So what do we know? Draw a little diagram for yourself. We know that we've got the vector that's going in an angle of 25 degrees from the horizontal in an anti-clockwise direction. We also know that the length of the vector is 7 units long. Now, if we've got this little diagram straight away, hopefully you'll see that, or start thinking Pythagoras and trigonometry, because we have enough information here to be able to figure out the horizontal component and the vertical component using trig. So we can say the cos of 25 is going to be a over 7. In other words, a is going to be 7 cos 25. A is going to turn out to be 6.3. Or we might say the sine of 25 is b over 7. B is then going to be 7 sine 25, and b will end up as being 3. That allows us then to be able to say, right, the vector written in column format is simply going to be the vector 6.3, 3.0. And there we've gone and created the vector in its component form. This formula over here might be a useful formula for you to remember in order to convert this. What I'd like you to do now is to go back again to that Vectors Introduction lesson, go and find page 9, and there they've got 4 examples where they give you the magnitude and the angle, and they want you to find the column vector. Go and try that, mark it, and practice these skills for yourself. That's all we're going to have for the introduction to vectors. Hope this is helpful. Goodbye.